Alright, spoiler alert, yes and yes. So, this holds for closed sets by definition, because we defined we defined closed sets to be sets which contain all their limit points. So, obviously, every point of every closed set is a limit point. Oh, well, wait a minute. So, that's actually sort of interesting. Okay, so we know that closed sets are sets which contain all of their limit points. Does that necessarily mean that every point of a closed set is a limit point? And that actually, the answer is no. Wait, closed sets of R2. Yeah. Zero is closed. And zero is not a limit. Wow, I almost really embarrassed myself there. Zero is closed and zero is not a limit point of zero. Okay. Well, why is zero not a limit point of the set containing zero? Well, that's because the set containing zero is in order to be a limit point. Well, I think we proved earlier in the chapter that isolated points are not limit points. But basically, that's the thing here. Zero is an isolated point here. Any neighborhood of zero, well, the only point contained in there is zero. The only point of this set, let's call this E. E is the set containing zero, is closed, and zero is not a limit point of E. Because you take any neighborhood of zero, and of course it contains the element zero of E, but there is no other element of E contained in that neighborhood. Therefore, it is not true that for every neighborhood of that, for every point of E, for every neighborhood of that point, there is a different point of E in that neighborhood. So E is closed and zero is not a limit point of that set. Why is E closed? E is closed because its complement is open. What is the complement of E? The complement of E consists of all points in R2 which are not equal to zero. And how do you know that that's an open set? Well, you choose any x which is not equal to 0 in R2, any point of R2 which is non-zero, then this point has some distance delta from 0 because it's not equal to 0. And then you consider the ball of radius delta over 2 centered at x. Then that ball it's an open ball, it's a neighborhood, and it is it's entirely contained in the complement of E, and it does not contain 0 because its radius is only delta over 2, so it cannot possibly contain 0, and so it is entirely contained in E complement. So every point of E complement can be surrounded by a neighborhood entirely contained in E complement. So every point of E complement is an interior point of E complement, which means that E complement is open. Or you could argue that you can write E complement as a union of these neighborhoods around points, and so E complement can be written as a union, an infinite union, but still a union. And the fact that it can be written as a union means that it's an open set. So E complement is open, and therefore E complement complement, which is E, is closed. Okay, so that was more work, or more detail, or more work than I was expecting. But yeah, so E is closed. So closed sets do not every point of a closed set needs to be a limit point of the closed set. However, closed sets, and that is not in that does not conflict with the fact that closed sets contain all of their limit points. So anyway, so that deals with closed sets. For open sets, for which the answer is yes, every point of every open set in R2 is a limit point. And of course, this is in R2, and I'll ramble about that a little later on. But for open sets, let E be open if X is an E, then X is an interior point of E. And that's because we define open sets to be sets which contain sets such that all of their points are interior points. Then for any neighborhood NR, I'll write this as NR X of X. So this is a neighborhood of radius R. Right, so this is a neighborhood of radius R centered at X, and I'll just write that as NRX. So for any neighborhood NRX of X, by interiorness, there is a neighborhood NSX, neighborhood of radius S of X, which is, wait, what am I doing here? Okay, to be an interior point, that means every point. Oh, let's pull up Baby Rudin. Interior point means that every point is contained in a neighborhood contained in the set. Went too far. Yeah, neighborhood. A point. Point is an interior point if there is a neighborhood which is contained in E. Okay, so I don't know what I'm doing with this NR and NS. That's not necessary. So X is an interior point of E. Then there is a neighborhood NR of X such that we have X is contained in NRX, which is entirely contained in E. Okay. Oh, I see what I was doing here. Oh, yeah, of course. So given any neighborhood NSX of X if we let delta be the minimum of R and S, then N delta of X is a neighborhood of X which is contained in both the neighborhood that we were given and S of X, because delta is the minimum of R and S, and so N delta is certainly contained in NS because it's at least as small as NS. So there's a neighborhood which is contained in both NSX and also contained in E. And it's contained in E because N delta X is contained in NRX, which we know is contained in E. Okay, so we have a neighborhood of X which is contained in both these sets. We also know that there exists, we know that since we are in R2, we know that there exists an element Y which is in N delta X, but which is not equal to X. And this being in R2 is really important here. But anyways, so this is in that. So there exists a Y which is in, it's in, let's see here, limit points. For every neighborhood there is a point. So certainly Y is contained in E, obviously. And it's also an element of this given neighborhood, which is not equal to X. Okay, so since this holds for every neighborhood NSX of X, so every neighbor, what have we proven? We've proven that every neighborhood of X contains an element of E which is not equal to X. And that's what you need to prove in order to prove that X is a limit point of E. So since this holds for every neighborhood NSX of X, X is a limit point of E. And this holds for any X in E. So hence, E contains all of its, or no. I almost said E contains all of its limit points, which is not true at all. For every single open ball in R2, the boundary of the open ball is a set of limit points which are not contained in the ball. So hence, every element of E is a limit point of E. And that's because every point of E, if you take any point in E and you take any neighborhood of that point, you can find another point which is in that neighborhood and which is also in E, but which is not equal to X. And that's what it means to be a limit point. And so every point in an open set is a limit point. Now it's really important here to note that that we needed to use the fact that we're working in R2 with what's called like the standard, was it the standard topology, the regular topology? Basically, the topology where open balls are, or where open sets are, the collection of opens, the topology has a basis given by open balls. So neighborhoods in R2 look like balls of a given radius. Positive radius, of course. But, yeah, so we need to use that in order to prove that there is another point Y in this neighborhood. Because obviously if you have an open ball, then there's like in any open ball there's uncountably many points. And so if you want to choose one that's not equal to X, like, okay, well certainly you're able to do so, because you know that there's uncountably many more to choose from. Where this is not true is scenarios where you have like isolated points. So if you think, consider the set of integers where you have this distance topology on it, and you consider the ball of radius 1/2 centered at 0. Then this is an open ball, so by definition it's an open set, it's an open neighborhood. But because you choose a radius of 1/2, the radius isn't large enough to include any other points. And so 0 is the only element of the set which is contained in this neighborhood. And that's a little strange to think about, because you're used to thinking of, oh, well, this is a ball of radius 1/2, so it contains all numbers from -1/2 to +1/2. But in this scenario, we're only considering integers. And so the only point in that open interval which really counts is the integer 0. But of course, 0 here, this is a neighborhood of 0 which contains no other integers besides 0. And therefore you have an open set which contains an isolated point. And so in this case, you have the it is not true that open sets. It is not true that every limit point. It is not true that every point of every open set is a limit point. It's not true that every point of every open set is a limit point. In fact, in that topology, are there any? You don't have any limit points at all in that topology, because you can't converge to anything. Because in order to converge, you need to have points that are arbitrarily close, which are not equal. And the closest any two things are is 1. And this sort of, you don't have to think about the integers at all. You can think of any set endowed with the discrete topology. And that comes up in, I think, exercise 10. And that's a really good example, so I'm sure I'll get around to that pretty soon. So go check that out if you want. That's a very good, that's a very important topology, and that's one that is necessary for a really good understanding of point set topology. But anyways, yeah, I'm sorry that this proof sort of started out rough. Started out with me saying things that weren't true. Luckily, I got to a point where everything that I've said is true, so that's good. But yeah, that's it. This should be like a real quick exercise, and I rambled on a lot and messed up, but here we are. We now have a finished, completely acceptable, fully rigorous proof.